Here we go. Bruh.
Ice cream lemonade and yeah, I don't like dairy in my cherry
Here we go.
Wait, are we doing decibels or intensity? Are they the same?
They're not the same. And this is intensity.
What?
This is intensity. Oh, you mean from the board?
Yeah.
Sorry. Intensity first, then decibels.
Like I need to know which one. Why can't you just like there's a lot of chicken. We just asked him this.
It was like
why he added intensity to the
or if you were like
All right. So everybody locked in on this question. Thumbs up if we're good.
We're here.
Okay. Have a conversation about this question.
This is square, so it's 3 squares. Oh wait, that is 1. Oh my gosh.
So if we move away from the source, is the intensity going to become more or less? By how much less? 1/9. Why? The R is squared. Good at that. So this is like 1/R squared type. Okay.
Wait, don't change that yet. Please.
Okay. Here is, okay, so you know how you throw a rock in a pond and it creates ripples like in a circle? Okay. Source of sound does the same thing, but instead of a circle, it's a sphere of sound wave going out. You okay with that? Okay. And it carries energy with that. That's what intensity looks at. Okay. It's how much energy there is per area. Here's my analogy for this. I'm going to compare energy to jelly. Okay. So if I am at the source, I'm going to be like eating jelly just straight out of the jar. Like, whoa, that's intense. Just hang with me, you'll get it. Now, if I take some steps back, that's like taking the same spoonful of jelly and spreading it over a cracker. Okay. If I take some more steps back, saying like I'm going to double the distance, I'm going to take that same spoonful of jelly and I'm going to spread it over a piece of bread. It's the same amount of energy, just spread over a bigger area. If I take some more steps back, I'm going to take that same spoonful of jelly and I'm going to spread it over a pizza crust. It's the same amount of energy. It's just getting spread out over a bigger and bigger area. So how are we doing with that? Okay. So the amount of energy that we would hear at a certain location is dropping off pretty quick because that energy is being spread over a bigger and bigger area as you go further and further away. All right Okay with that? Okay. Okay. Tell your neighbor.
They're making that's what it sounds like. There might be some grammar where you can't have like two ing words back to back. Because that just doesn't sound right. There should no. There just needs to come Jamie. Actually, yeah. Get your commas correct.
Correct answer is.
I don't know. Wait, hold on. Don't tell me yet.
Are you ready? I was waiting for you.
Oh, my bad.
Okay. Intensity is the thing that mathematically makes sense. If one guitarist is going to have an intensity of 400, three guitarists would be 400 plus 400 plus 400. Three times 400 gives you 1200. Crazy cat. Okay? Charming chimps.
Wait, what's the times 10 thing?
We'll get there. We will get to the weird stuff. Okay? Everybody good with this? So, intensity mathematically, we comprehend that. This makes sense. This is a good comfort zone. Okay? Tell your neighbor. Correct answer is C. Okay? If you double the perceived volume, it's not what we'd expect. We'd expect if you're like, oh, that's twice as loud, that there would be twice as many like twice as many guitarists. It'd be like, but turns out when we measure, if we like measure the perceived volume, like, oh, that's twice as loud, it turns out to be 10 times the intensity. Just kind of how our body is wired. Okay. So if you double the perceived volume, it's 10 times the intensity. Okay.
After Jamie. Okay.
Yep, you did.
No, I think it's just he's a question.
Okay. Let me do a quick review here. Okay. So one guitarist has an intensity 400. Three guitarists has an intensity of 1200. Single guitarist has an intensity of 400. What is the intensity for if you double the perceived volume? 4,000. We're doubling the perceived volume. You have 10 times the intensity. So last one was 4,000. So if we double the volume, what must we do to the number of sources? 10 times the number of sources. Okay? Because intensity and the number of players go hand in hand. Okay? If we need to multiply by 10 to the for the intensity, we need to multiply by 10 by the number of sources. Yes, but what we're doubling in the question is doubling the perceived volume.
Yeah. Wait, so double perceived volume.
Multiply by 10. 10 times the number of sources, 10 times the intensity. Tell your neighbor. Correct answer is? Correct answer is dangerous dinosaurs. Okay, 10 times the number of sources. 10 times the intensity. Number of sources and intensity go hand in hand. Okay, so I want to do a proof of concept. If you could get out your cell phones. You're looking for a YouTube video. Play 256 hertz. Okay, you're looking for the YouTube, not the water one. You're looking for this title here. 256 hertz, sine, tone, amplitude. 1. Okay, it's a black screen. For me, it's the third one down. It's for an hour. It's for an hour. Okay, that's what you're looking for. Okay, go ahead and just get that ready to go. Okay. I mean, you can, but I'm gonna have you turn it off here in a second. Okay. Now, this experiment has some flaws. Number one, not all of our speakers are identical. Number two, the location of all our phones is not in the same spot. But we're gonna run it anyway. Hold your phone up if you have that ready to go. Yeah, all the way up. Okay, if I point to you, you're part of the group. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. The rest of you hold on. You'll play here in a second. Okay, I'm going to do one. Okay, register that. Okay. Everybody, people I pointed to, play. Twice as loud. Yeah. Okay. Pause. Okay. Now, I'm going to play mine. This is where the rest of you are. You all jump in. We're going to assume that 20 phones are going to go here. Okay, here's one. Rocket yours. That's two. So going from 1 to 2 did not double the volume. Okay, so now here's the volume for 2. Everybody hit play. Going from 2 to 20, double the perceived volume. It's just kind of how our bodies are wired. Okay, go ahead and pause. One to 10, or from 2 to 20. You gotta multiply it by the number of sources by 10. For that. Okay. I used to do this with dog whistles and it got really annoying. Okay. Give that one a shot. Tell your neighbor. Correct answer is A. We have the perceived volume, divide by 10. Okay. Now, the fact that there's this pattern that we have to multiply by 10 to double the perceived volume, that screams logarithms.
You're kidding.
Not kidding. Okay, now here's taking you back to when I was in high school. I could rock the socks off of these things. Okay, because I memorized this pattern. Like I remember studying for this, like, okay, the B gets bigger, the X gets smaller, and the Y flips over to the other side. And so when the test came out, I would write this on the top of my page. And I would get A's on these tests because I could regurgitate this pattern. I would have no idea what I was doing, why I was doing it. I just knew this pattern worked and it got me good grades. And that was satisfactory enough. Kind of the problem with our educational system. It doesn't go for understanding. It goes for, can you spit out what was fed to you? Okay. So why this class is hard, because I try to break that. Okay. So my hope is to give you, if you don't have a handle on how or why we do logs, that this slide is going to give you a better understanding of that. Okay. So if I have 10 to the second, what does that equal? 100. Okay. If I have 10 to the sixth, what is that? Oh, wait. You know what that is, but hold on. So if I say log, and I'm going to assume we're always doing base 10. Okay. Log of 100 is equal to what? 2. Okay. 10 to the 6 is equal to what? It's equal to a million. 6 zeros. 1 with 6 zeros. If I do log of a million, that's equal to what? 6. What is it that the log focuses on? What is it that it tells me? When I hit the log button, it says, it answers, it spits out what? The power or the exponent. 10 to the what exponent? Like this is what the whole point of logs do. Is it says 10 to what exponent? It's the exponent that we care about. That's where you get this adjective exponential growth. It's focusing on the exponent. You okay with that? Okay. So if I had 50,000, I don't want you to do this in your calculator yet. I just want you to estimate. What do you think that answer is going to be when we stick in 50,000 and hit the log button? Have a conversation. You know it's going to be somewhere between what and what. Okay. So 10,000 is going to, when you do the log of that, it's going to equal 4. And 100,000, that's going to equal 5. 50,000 is between that. It's going to be somewhere between 4 and 5. You okay with that? It's not going to be 4.5 because logarithmic scale is not linear. Okay? This is where you have to use a calculator. Go ahead and pull out your calculator. And what is it? 4.69. Okay? Prior to calculators, people would have like these catalog books that you would have to flip through to find the log. Yeah. Yep. Okay. So this isn't something you do in your head. This is something you use a calculator. But I wanted to give you like an intuitive feel for what it is you're doing with the logs, if it wasn't there already. Good. Okay. So the fact that going back to hearing, like, oh, that's twice as loud, and then we measure and it's like 10 times the intensity. That screams, hey, we should use logs. Okay. So the Richter scale is also a logarithmic scale. Okay. So let's say we get hit with an earthquake that has 4 on the Richter scale. Okay. And then a second wave hits and it's 6 on the Richter scale. Most people are like, okay, increases by 2. Folks, that increased the exponent by 2. That's like 10 to the 4th to 10 to the 6th. That is 100 times the intensity. There's 100 times more energy in that second wave of earthquake than there was the first. You right with that? Okay, so that's what the exponent tells us. All right, so you have 4 blaring car horns producing a total sound of 70 decibels. What is the intensity of that sound? Okay. So I'm going to use this equation. Okay. So I've got 70 decibels. It's equal to 10 times the log of the intensity I'm looking for over the threshold of hearing. Okay. Solving for I, so I'm dividing by 10. So if you know how to do logs, you can do this in your head. If you don't know how to do it in your head, you can do it on a calculator. What are you doing on your calculator? Yeah. That's just the threshold of hearing. That's just a constant. Yep. Okay. Inverse log is times 10 to the x. On your calculator, you hit the second button or shift and then the log button. Okay. And that's going to give you 10 million on your calculator, which is just 10 to the 7th. Okay, you're welcome to do that on a calculator or not, or you can do it in your head. When we bring this over, we are multiplying these two, so when we multiply, we add exponents. So we get 1 times 10 to the negative 5th. The units on that is watts per meter squared. All right with that? Watts per meter squared. Okay. All right, there, getting the number. I mean, it's fine. You can go times 10 to the negative 5th. It's fine. Jesse.
Can you explain the part where, like, the part of the equation where you said 70 was a log of that? How did you get to the 10 to the 7th power?
So depending on your calculator, you do 7, then second log button, or it's like second log button 7, depending on how your calculator is.
We can still take that. So if you put 10.
You go, okay, we're trying to get the log the other side. Mm-hmm. So your calculator, where's your log button? There it is. Okay, so 7. And that's 10 million.
But what's the point of doing that?
It gets the log to the other side.
Oh, now we understand now. Sorry, it's been a high top second blog.
Okay, good. So that's the intensity for 4 car horns honking. Follow-up question is, what's the intensity for 1 car horn blaring? If we know the intensity of 4 is this, how would we find the intensity for 1? We divide by 4. Intensity makes sense. Okay? The number of sources and the intensity go hand in hand. Okay? So we would take 1 times 10 to the negative 5th, and we would divide that by 4. Okay, I recognize this is improper scientific notation. Just roll with me. Okay, 0.25 times 10 to the negative fifth. So it's just divided by 4. It's a fourth of what your kid. Okay, everybody good with that? There are 4 cars making this. Okay, now there's one. I just want 1. Okay, so now what? Before we calculate this, how many decibels is that going to be? 4 cars made 70 decibels. 1 is going to make what? Just estimate, guess. It's going to be wrong, but I just wanted to like show you. Okay, so I'm using this equation. So yeah. Oh, that's hilarious. Okay, so yeah. All right. So are we good? Is it set up here? What? I haven't come to the answer. I'm just. Okay. So this is log of 2.5 times 10 to the 6th. Oops. When you use a log of that, you find that to be 6.4. So it's 64 decibels.
Wait, where's the log? Did you take the log of the 2.4?
I did. Yep. That is. Yep. Okay. 1 car horn. Sorry. 4 car horns, 70 decibels. 1 car horn, 64. What? Right. Okay. It is not sorry, it's not linear. It is not, it does not make sense. You need a calculator. Okay? You need a calculator to do logs. Okay? There is a pattern though, which we will talk about here momentarily. Okay? But to actually figure out a problem with how many decibels you've got to use an equation. Are we good? Okay. Ready to move on from the math? Okay, here we go. That's the math. All right, so we have 1 car horn had a volume of 64 decibels. Okay, how many decibels if we doubled the perceived volume? Like, oh, wow, that's twice as loud. What would the decibel reading on that be? Tell your neighbor. Correct answer is not C. Correct answer is A. This, okay, here's the deal. Ready? When we double the perceived volume, we add 10 decibels. We add 10 decibels. With, listen, ready? This is different than intensity and number of sources. Intensity and number of sources, we multiply by 10. Decibels, when we double the perceived volume, we add 10. Okay. Okay. Adding 10. We're multiplying by 10 for intensity and number of sources. Okay. So give this one a shot. This is a good, I like this question quite a bit. Tell your neighbor.
Is this what you said? I was trying to write it fast. Oh, yeah. That's what I wrote.
2 decibels. You add 10.
Okay, so to double the perceived volume, you need more sources. 10 times more sources, but only 10 more decibels. Right, so it has to be.
So this is the same thing as this. 2 intensity. And
Okay.
okay. Welcome. What do you say? Correct answer. I hear B's and D's. B's and D's. One of those is right.
So which one? It's not yet to E.
No. B or D. One of those is right. One of them is wrong.
So it doesn't have to be 8, but it's just depending on the number of horns. So which one is it?
Okay, so when we are doubling perceived volume, we are multiplying the number of sources and the intensity by 10. When we double the perceived volume, we add 10 to the decibels. You got the adding 10 to decibels. You're multiplying the number of sources and the intensity by 10. D, dangerous dinosaurs. I sure will. Ready? When you double the perceived volume, you multiply the number of sources and the intensity by 10. And you add 10 to the decibels. decibels. Good? Okay. Tell your neighbor what you think.
Intensity unit is intense.
Did you hear about the circus fire? It was intense. All right. So here we go. Ready? We're going from 95 to 85. We're going to take this in steps. Okay. We subtracted 10 decibels. Therefore, what do we do to the intensity? Divided by 10. When we go from 85 to 75, we subtracted another 10 from decibels. So therefore, what did we do to the intensity? We divided by 10 yet again. So if we divide by 10 divided by 10, that is divided by 100. C. How we doing? Okay. All right. This chart, don't get overwhelmed. Okay. Here's what okay. Here's the decibel level. Here's the intensity level. Every time you go down a row, you're doubling the perceived volume. Examples of this I'm not a huge fan of, but whatever. So we add 10 to our decibels. We multiply by 10 to our intensity. Every time you go down. Okay. Adding 10 to decibels, multiplying by 10 for intensity. Okay. Trying to make some connections here with our human hearing. So this chart is frequency, so low pitch, high pitch, and intensity, quiet, loud. Okay. We have a hard time hearing quiet, low frequencies, but we pick up really well quiet, high frequencies. This is the threshold of hearing. So this is why sound tests usually have high pitches, like, okay. Threshold of pain, this is where you're like busting eardrums, okay, kind of across the board, okay. So talking about busting eardrums, let's talk about hearing protection and damage to hearing. We all know that loud sounds cause damage, okay. Here's the thing that was eye-opening to me. It's the fact that it's not only a fact of volume, but it's also an effect of how long you've been exposed to that sound. Okay, so lawn mowing isn't that loud, but how long are you exposed to that sound? How long depends on how big your yard is. So like hearing protection for lawn mowing is a good idea. Listening to your music. How long do you listen to your music? And how loud do you have it? If you want to go into a good, secure career path, audiology, you're going to have a lot of patience because people listen to their music a little too loud for a little too long. Huh? Good at that? Okay. This is just for funsies. This is looking at different animals. We like rock the socks off of the low end. Elephants are the only one who beat us, but like on the high end, so like water mammals like are porpoise, dolphin, whales, beluga whale. That's Dory, like the white dude. Yep. Get to that. Okay, got a worksheet due on Monday along with a lab quiz.